So this is my cheat sheet. It covers motion, essentially. And in terms of the topics it covers, we have linear motion, linear, projectile, circles, circular, energy, momentum, hints, and gravity. And I'd just like to show you quickly how I use this cheat sheet. So linear motion. Essentially, camera's shaking a bit, so let me fix that. Essentially, linear motion, the study of motion. And what is motion? Linear means linear is one direction, motion is anything that moves. So linear direction is about getting from point A to point B. So the variables are actually kind of intuitive. What do we need to get from one place? Well, we need a starting speed. We need all the stuff that happens in the middle, which is acceleration. And then we need a final speed. Then, obviously, we covered some distance, x, and the x is distance. And it took some time, t. T equals time. And that's where these 5 variables came from. Because that's pretty much everything there is from getting one place to another place. Easy. Now, these are just useful formulas. That's all they are, of converting, if we have our starting velocity and acceleration and time, we can get final velocity or distance. If we had our starting velocity and final velocity and time, we could get the distance. Or if we had starting velocity, acceleration, and time, we can also get the distance. And so on and so forth. You get the idea. But the interesting thing is all formulas only involve 4 of the variables. You don't need all of them. So if we didn't care about time, if the question made no mention of time, we could just look for equation which didn't have time. This one doesn't have time. That would be v squared equals u squared plus 2ax. And if we had 3 of the variables, say we had v, u, and a, we could always find the 4th one, because this is an equation relating them. So that's how we use these formulas. We figure out what we have, say u, starting speed, and time, and say acceleration, and what we need, x. Okay, this is what we have, this is what we're looking for, and we just look for UTAX, or XUAT there, and that's the formula we would use. So, quickly, this is just distance. This is our usual distance formula because we usually have velocity, acceleration, time. This is one where we don't care about time at all and we're just trying to look for the distance or the initial or final velocity. This one is if distance doesn't matter and we're just trying to figure out what speeds they're moving at. And this one is if we don't have the acceleration and we just use the average speed. That's how I think of them. That's how I use them quickly. So let's find an example. Okay. This is the 2010 exam. No, 2007. So this will be the reading time for this. Fred is riding his bike on a level road at 5 meters. The tail light breaks off. It takes 0.4 seconds to reach the ground. How far above the ground was the tail light when it was attached? So what's happening is, okay, here we have a tail light. Okay, and because it takes this much time to reach the ground, we know we're only looking through vertical eyes, vertical vision. I don't understand anything horizontally. I only understand things in the vertical place. Okay? So what's the initial vertical velocity? 0. It's not moving vertically at the beginning, it's moving horizontally. What's the acceleration? It's 10 towards the ground. And what's the time? 0.45. And what are we looking for? How far above the ground? X. So we have x, u, a, t. What do we need? X, u, a, t. Winner formula. So x equals ut plus half at squared. X equals ut, which is 0, because u is 0, plus half times 5 times 0.45 squared, half times 10, acceleration is 10, equals 5 times 0.45 squared. And I don't have my calculator, so I'm just going to skim that. But that's how you use this. That's how you use linear motion. So projectile motion usually comes of one of 2 types. This is usually. Sometimes they do funny things. But if you're trying to figure out this distance, you have to decide really quickly, quite early, if you're going to look at horizontal or vertical first. Because only one of them is going to give you time. Okay? Because, We can figure out how long it takes, and then we multiply by the speed to give us that place. So you need to figure out which one to go for first. And so I kind of did it for you, briefly. Because you think about, okay, I say it quickly here. Anything that hits the ground, you're going to start with vertical, and if they give you the height. If anything starts from the top, from beginning and then lands at the same place, probably vertical. If they're asking you for a maximum height, go vertical, because these are all vertical bits of information. You need that extra bit of information. On the contrast, in contrast, if you shoot at, like say, a car across and it hits a wall X distance away, you can use horizontal then, because that extra piece of information is horizontal. And if for some reason you have both of them, then it might require simultaneous equations, or you can use either. So, I'll show you why. If you consider us shooting this V with theta, then comparing vertical and horizontal, our initial speeds are, vertical is V sine theta, and V cos theta, U cos theta. Okay, our acceleration is usually minus 10, and the acceleration for horizontal is usually 0. We're usually trying to find something, be it x or t. Here, we just need one more piece of information. Just like I said, we need 3 bits of information. So here, the extra bits of information is, if we know the height, then x equals that height. If we know it lands on the ground, then x or height equals 0, and that tells us we can find t. If we know this, we know that the final velocity, the special point about going up to the top, is that the velocity equals 0 at the top. So we can get that extra bit of information, v equals 0. And then if we were looking for x, we can use v squared equals u squared plus 2x, because we have v, u, a, x. Now on the other hand, if we have this piece of information, we know x equals d, and therefore we can find time here. And once we find time, we can just sub it in to find out how high above the ground we are, because that's usually what this question asks. Okay, so let's find a question and just briefly outline it. This question, I look at it, I know our initial speed, I know the horizontal distance. Okay, what is the time of flight of the paintball? It's this one. X equals 127, U equals 40, cos, because we're going horizontal. Cos 25, and then A equals 0. T. Then we just use XUAT. Easy. Question solved without reading it. What is the value of h of the maximum height above the firing level? So, we know here that v equals 0. So u equals 40 cos, sine 25. This is like vertical now. I keep getting confused. Acceleration equals minus 10, and v equals 0. And we're trying to find x. V squared equals u squared plus 2x. It's so easy. Yeah, so that's how I use projectile. And this is just a method of converting, telling you what the vertical velocity is and the horizontal velocity is if they give you v and theta. So vertical is v sine theta, horizontal is v cos theta. And when asked for final velocities, the way to do this question is to find the final vertical velocity and the final horizontal velocity and add them together. Usually the final horizontal velocity is the same as the original because a equals 0. And you can usually get the final vertical velocity by using v squared equals u squared plus 2ax. Because they usually give you the initial one. Like for example, they tell you that it lands where it was. That means x equals 0. Yeah, if it lands where it was, then we can find x equals 0. We can get rid of that, and they usually give us the initial velocity. And that tells us the final velocity. Then to put them together, the angle is, using Pythagoras, square root of a squared plus b squared, that plus that. And that's the magnitude. And the angle is the inverse of tan. A and b, vertical and horizontal. Awesome. Circles. A lot of people have trouble with circles, but it's not that hard. Essentially, it's just free diagrams, okay? This will be all forces. This will be net force. This will be drawing circles. If we draw a circle and we are object moving, we know it must be going inwards. Otherwise, if it wasn't accelerating inwards, it just go in a straight line. So it must always be accelerating inwards, okay, to be in a circle. Note we have nothing to do with force yet. We just know if it's in a circle, it must be accelerating inwards, and acceleration equals A equals V squared on R, which I put over here. Now, if that's true, the net force must be M times that. Force equals MA equals MV squared on R. Therefore, the net force must also be going inwards. Force. Okay, so that's going from one direction. Now let's look from the other direction. If we have all forces and we know it's going in a circle, well, let's just label all forces. Let's say we have one of these just touching questions. One of these, I'm going around here and they just touch at the top, and this used to be so hard for me, but now it makes sense. All the forces acting on it are mg, and the normal force is pushing on it from down the top. Okay? So our force equals mg plus n. Mg plus n. But when it says, what's the minimum speed? This is when we're going all around and we reach the top and we're just about to fall off. We're almost just touching. We're not getting any force from there, and n equals 0. So now if we know all forces are this, and now n equals 0, and so therefore our force going inwards is now just mg. And we know, because it's going in a circle, it must equal F. And we know F must equal mv squared on R. Therefore, this is all forces, must equal the net force, must equal mv squared on R. That may confuse you a little bit, but it's like this is all forces, and therefore the net force must be this for it to move in a circle. It's essentially the centripetal force. And so I did it down here. If we're going around a loop-to-loop, force equals mg plus n, but n equals 0. Crazy. Therefore mg equals mv squared on R, and we can solve that. We can cancel the m's, we get g equals v squared on R, v squared equals g r, therefore v equals square root of g r. But I'll let you do that on your own. So another one for circular motion is if you're going around this loop. And all of a sudden they feel weightless at the top. So now, what we need to do is figure out what the forces are again. We have mg going down, and we have the normal force pushing you up. Okay? So the force going inwards, the net force going inwards, is mg minus n. You see? mg down minus n. And that must equal mv squared on r. They're going in a circle. The cool thing is they're feeling weightless. Apparent weightlessness means, how do we know we weigh anything? Because this chair is pushing me up with a normal force. So if this chair wasn't pushing me up, if I was just falling, I would have nothing pushing me up. I would have no normal force. I'll put apparent. Yeah, no normal force. So, this is 0. mg equals mv squared on r. Whoa, again, crazy. You see that exclamation mark? How crazy is that? And finally, the incline question, which is quite difficult sometimes if you don't know what's happening. Let's say you're riding a bike and you know you're moving in a circle. So we know there must be a net inwards force of mv squared on r, because I've repeated that so many times. You need to figure out what the net force on this guy is. Well, what are all the forces? The forces are mg going down and a normal force going this way. If this is theta, let me show you, and we make that 90 degrees, and that must be 90 minus theta. If we make that 90 degrees, this must be theta. So if we look at the normal force again, it looks like this. Normal. This is theta. This is our direction. And since it's not moving down, the magnitude of this must be exactly cancelling out our gravity force. So upwards must be mg. Okay, so what's x? Well, we know tan theta equals x on mg. Therefore x, take the mg over, equals mg tan theta. That's our inward force. Our inward force is this thing, x. Our force is mg tan theta. Force equals mg tan theta, which then equals mv squared on r. Bossed. Okay. I should show you a question. I'll show you how to do it. Where is the circle? This doesn't have a circular motion question. Okay, but I kind of covered all of that there. 2007 people were lucky. Okay, energy. It's a way of converting energy. Energy is essentially... it's a way of converting one topic to another. Sorry about this thing. One type of system to another. Okay, I can't explain it. Let me show you with a diagram. mgh is the amount of energy we have up here. It's potential because we haven't used it yet. Now, if we go on a slide and we end up here, we've lost all that energy. Where's it gone? Well, we weren't moving here. Now we're moving with some velocity here. So it's gone from potential, or gravitational potential, to kinetic. So therefore mgh equals half mv squared. Now say we went and we hit a spring, and we compress this spring by x meters. Then, and we stop moving, and our block stopped moving. We've lost all our kinetic energy. It's not moving anymore, but we've stored all the energy in this spring. And that means we now have half kx squared. Finally, if we shoot the spring off and another block goes again, it comes out and now it's moving. We've lost all the spring energy. The spring's back to full size length, but now this block has a velocity, and it goes back to mv squared. This is a very contrived situation, but I'm sure you see these kind of questions. And if it goes over some rough patch, and you know there's some kind of force, and you know how far it travels, we know, and it grinds to a stop. You know, this block is stopped. Where's the energy gone? Work has happened. Work is force times distance. The work has been the ground pushing our block back. And that's why this equals this. Energy, in a nutshell. Yeah. I put force equals kx for spring, and I'll show you an example of that. That's not very hard. We're just saying if we compress a spring by x, the force equals kx. And I'm running out of time. I have 2 minutes left to explain to you all of motion. So I got to get my act together. The laboratory attaches a spring, stiffness, so K equals 20 newtons per meter. The stretch length, he hangs it vertically and attaches the mass, so the new length of the spring is 0.6. Assume the mass, the spring has no mass. What is the value of the mass he attached? If the mass is mg, we know our force must be must be kx. Force equals kx, going upwards. That's what's happening to the spring because it's being stretched. So we just sub in k is that. We sub the length of the spring is that, and therefore that equals mg. Kx equals mg. So the mass equals kx on g. How much potential energy do we have stored in the spring? Half kx squared. Half kx squared. Half k x squared. Easy. 40 seconds left. Momentum. I think I'm going to have to go over time. So momentum is mass times volume, mass times velocity equals force times time. So where's a good question for that? That's not very hard. One block hits another block. Big guy, big blocky guy, hits you. Small guy. Okay, you're a little bit big too. He has a mass times velocity, and if afterwards he stops moving and you're moving, we know that was a collision. And collision is either momentum or energy. Most of the time it's momentum. So here, our initial, I should say it was 100 times 10 meters a second equals 1,000, and let's say you weigh 50. Okay, so he's moving at 10 meters a second, and he weighs 100 kilos. What's his momentum? 1,000. And if afterwards you're moving, we know that all that momentum, and the momentum of the first system equals the momentum of the second system. First system was 1,000 momentum units. What is that? Kilograms, meters per second. And then that equals mv again. That equals your mass times your velocity. 1,000 equals 50 times v. Cancel that over. V equals 20. Yeah. And now if you want to lose all that, we'll say someone was pushing on you with an average force of 5 newtons. How long would it take for him to stop you moving? We use momentum again. Your momentum equals 1,000, let's make it 50 newtons, equals mv equals F times t. F is 50 times t. Cancel, we take it over, and we get t equals 1,000 over 50. 20. Take you 20 seconds to stop you moving. Hints. Motion, velocity, energy, momentum. Okay, so this is a way of converting energy to velocity, and energy to momentum, motion, we can get pretty easily by using this formula. That's how they're all interlinked. Just never forget they're interlinked. And inelastic collision means loss of kinetic energy, so all you need to do is use this formula. If after a collision, the total energy, like energy of this plus energy of this, versus energy of this plus energy of this guy, is different, then it was inelastic. If it was the same, then it's elastic, because you kept all your energy. Graphs. This is useful. When you have any graphs, what is the gradient? The gradient is y on x. What is the area? Y times x. How is that useful? If we take a velocity versus time graph, the gradient is v on t, and we know that's acceleration. So the gradient of this is acceleration. If we look at the area, that's v times t, which is distance. The area under this curve is the distance between 2 points. So I've done this for momentum is force against time. So if you took the area underneath there, it'd be momentum. Or if you did force against distance, you get work or energy. If you had, what's it say there? I think you can't read it, but it says stress of a strain, the gradient is Young's modulus, and the area is energy per unit volume, because that's what they are. And finally, gravitational, force against radius or force against distance, it is the amount of energy that B has more than A. Because the further away you are, the more potential you have to drop in. So you notice they're further away here. Even though it's at a lower point, they're further away. That is how much more energy that B has than A. So an example of this here. Estimate the work done by air resistance force on Amelia when she was falling 500 meters from the plane. You don't know the entire thing, but we're looking for work, and we have a graph here. Fallen how far? 500 meters from the plane. We don't know anything. All we know, she's falling. This is a force of air resistance. So what is the energy, the work? It is the area under here, because this is force times distance. So that is how much energy air resistance did on Amelia from the distance of 0 to 500. Show you the question again. Yeah. So to calculate it, it's roughly, I'm going to do that block plus half of that block. So that is 20,000 plus that's 200 times 400, 80,000 plus, so that's about 200 again, times 600 plus 120. 1, 2, 3, 1, 2, 3, 4. Yeah. Joules. You add these together. And we're done with that. Gravity. So slow. Please forgive me. Okay. Blah. I know the radius of one. I know the radius of another. That's all I have. And I know, I should probably read it. It has approximately the same mass. So they both have the same mass. So we're asking, Eris, which has the same mass as Pluto, has a radius of 10.5 times 10 to the 12. And Pluto has a radius of 6 times 10 to the 12. What is the gravitation of the Sun on Eris on Pluto? So let's just call it the force on Eris, like the force of Eris. And then I do it like this, because it makes more sense to me. The force on Eris, here's the force, is Gm1 m2 on r squared. So we got G m1 m2, I don't really care with that, on r squared. Eris is 10.5 times 10 to the 12 squared times 1 on the force of Pluto. And what does that mean? 1 on the force of Pluto means we just flip it upside down. So it becomes r squared on G m1 m2. And this time r is 6 times 10 to the 12 squared. That's much easier. We cancel all this stuff. I can cancel out these 12 squared, because we've got the squared there. And we're left with 6 squared on 10.5 squared. I don't know what that is. Let's just say it's 6 on 12, because I don't have a calculator on time. It's about 1/4. It's a bit more than 1/4. It'll be A. How many Earth years does Eris take to orbit the Sun? What did I do? Yeah. How many Earth years does Eris take to orbit the Sun? Well, we know the force equals that. So the way to use this is, I didn't explain it to you, but gravitational field is equal to each of these things. Force, acceleration. Force is equal to each of these things. So if they ask for force and you have mass, you use this formula. If they ask for force and you have velocity, you use this formula. If they ask for force and you have period, you use this formula. Now, what are we looking for? They're asking us for period, and we have mass. So if we have period and we have mass, we use these two. Gm1 on r squared equals 4 pi squared r on t squared. We rearrange it. T squared equals 4 pi squared r cubed on Gm1. Oh wait. And we know the period of Pluto around the Sun is 248 Earth years. Okay. So, therefore we know that I can't explain this to you quickly. Okay, so this is t squared. Therefore Pluto equals 4 pi squared r cubed on Gm1. Okay, so the regular one. And now if we want Aries, this equals square root of 4 pi squared. But now the ratio, we have the ratio of the radiuses. Aries is 10.5 on 6 times Pluto's radius. So we can replace r with that, Pluto's radius. This is radius of Pluto. This may confuse you. And then we take that part out. We keep the square root. And then the rest of it is just what we had originally. So times what we had originally. And this equals 248 Earth years. And then we just multiply by that. And that will tell us how many years. So forgive me if the last part confused you. I hope it made sense. Can't be completely sure. But the rest of it should work quite well. I hope you enjoy the cheat sheet. Make good use of it. Good luck for the exams. Thanks.